one segment left, and that's to finish a proof of the assumption we made that the assumed spherical Earth looks to other objects like a point mass with the mass of the Earth all at the center of mass of the Earth. That if we are in orbit, gravitationally, it looks to us like we're not in orbit around an Earth-sized thing, that there's no difference between that and a point of mass equal to the mass of the Earth located at the center of mass of the Earth. Justifying this is going to take a little bit of math, a little bit of calculus. The derivation is in the book, but I wanted to kind of talk about it and sketch it a little bit and outline it for us. Okay, so first step is to, first step is to make a simplification to our problem. Instead of thinking about an entire sphere, a solid sphere worth of mass, let's only think about a very, very thin spherical shell, like an inflatable ball or a balloon. It just has that skin and nothing else inside. All of the mass is around the surface area of this spherical shell. And we are a point somewhere away from that sphere. We're trying to figure out what is the gravitational potential energy at the point where we are due to this shell of mass. So let me show you the diagram from the textbook so we can kind of agree what's going on. Okay, here's the story. We've got that spherical shell, and we are here at point P. For our purposes in the calculus we're about to do, capital R is the radius of the spherical shell. So it's not going to change. It's the same spherical shell the whole time. Capital M is the mass that is distributed over that surface area. So again, that's also constant. Lowercase r is also constant. It's the distance between the center of the sphere and point P. So we're not moving point P, we're not moving the sphere, so lowercase r is also constant for this derivation. So okay, so what can change? Phi, the angle, and s. We are considering, we're going to do Riemann things with rings of mass, this pink highlighted deal here. A ring of mass that is all lowercase s away from point P. Imagine this little chunk of mass right here on the edge of the sphere. The distance between that mass and point P, that's s, lowercase s. And since it's symmetric, all of those points in that pink ring are lowercase s away from point P. So this diagram's in the book. You can refer to it at your leisure. I wanted to share it so that we're looking at it and we can talk about it. But I'm going to turn it off now so that we can see the whole screen instead of just the tiny version. The other part of the diagram is some geometry, and I guess while we've got it up, we should look at that too. We've got the center of the sphere, point O, and a radius away this little chunk of mass right on the edge of the sphere. The angle between the distance, the line between the center and point P, the angle between that and this point here is phi. So this distance is hypotenuse times, okay, so that's adjacent, so that's cosine, r cosine phi. This distance here is r sine phi. The total distance from the center to point P is r. So this distance is r minus capital R cosine phi. So that's what we're doing, is setting up a way to express S in terms of R, or vice versa. Because we can do Pythagorean things with this right triangle. The hypotenuse S, short leg r sine phi, long leg r minus r cosine phi. Okay, so that's the story of the diagram. I'm gonna, stop sharing my screen. Okay. So that little chunk of mass dm right on the edge of the sphere. At point P, we feel some gravitational potential energy according to this little mass. Okay, so we have potential energy negative g. M is the mass that lives at point P above the sphere. dm is the mass of that little chunk in the ring that we're talking about. gmm over s. That's not a 5, that's an s. That's the distance from point P to this mass. Let's call this du. Okay, fine. So we need to add up all of these masses in the pink ring, all the way around that spherical shell at the same kind of height. All the points that have the same distance s away from point P. So we need to know the sum, we need to know u of that ring is minus gm capital M, which is the mass of that ring in the thing. Okay, now that ring is a strip of paper that is a little bit wide times a circumference. It's an area. It's a strip of paper that has an area, because this sphere that we're talking about, it's only an area. So the mass that lives in this ring is the fraction of the total mass, m, that is, it's the same fraction of the area of the ring to the total area of the sphere. Let me say that again. This ring has some small area, and whatever fraction of the total surface area it has a mass that is that same fraction of the total mass. All right, so in order to figure out what the mass of the ring is, all right, well, okay. So the mass of the ring compared to the total mass of the thing is the same as the area of the ring divided by the total surface area of the sphere. Okay, so we want the mass of the ring, so I'm going to multiply both sides by m, and we know the area of the entire sphere is 4 pi r squared. Now, the area of the ring is a tricky thing. The area of a strip of paper is its width times its length. Its length, if we cut the ring, that pink ring in the diagram, if we cut it and laid it out, it would be as long as its circumference. All right. So the area of the ring is circumference, capital C, that's trying to be, capital C of the ring times the width of the ring. Just going to call it W for now. Now, the circumference of the ring, its radius isn't little r, and it's not big R. The radius of the ring is the distance from the line between P and the point and the center. Let me see if I can draw this really quick. That line and this point we're talking about. The ring has this radius, which, if you remember that triangle diagram, that was 2 pi r sine phi. That's the circumference of that ring. Its width is the width of a little bit of arc length as we change the angle. As we change, I'm going to draw it big for effect. So here's the center. As we go from here to here, that arc length, which is r d phi. That is the area of the ring, a length times a width. Okay, equals. The area of the ring is 2 pi r squared sine phi d phi m all over 4 pi r squared. So the r squareds cancel, the pi's cancel, and a factor of 2 is left is all. The mass of the ring is 1/2 m sine phi d phi. Okay, fine. With me so far? So the mass, negative g, the mass at point P, the mass of the ring is this junk we just wrote. Total mass of the sphere, sine phi d phi, all over S. Now, so that's one of the rings, but we have a sphere's worth of rings. As we go from the very top of the sphere, the rings get bigger towards the diameter, and then they get smaller again. We have a whole sphere's worth of rings. Phi, at the very top, at the north pole of this sphere, phi is the angle between the line, and so it's 0. And it's going to go all the way around the sphere to 90 degrees and then down to 180. So theta is going to go from 0 to pi. S the smallest S is going to be is when the point is as close to point P as we can get. The center is R, so the distance between P and the point in question, the ring that we're talking about, is S, and its smallest value is R minus capital R, right? Because we've got this radius. Its largest value is when we're as far away from point P as we can possibly get, which is another radius away plus R. So S is going to go from R minus R to R plus R. In order to integrate this, we've got to pick a variable. I don't want to have phi and S rattling around in my integrand. And that's what that business with the Pythagorean theorem was about. S squared should be r minus r cosine phi squared plus r sine phi squared. And refer back to that Pythagorean, picture to see where this comes from. Let's FOIL out. R squared minus 2r cosine phi minus r cosine phi r squared plus r sine squared r squared sine squared. So this is plus because we're squaring the negative. And then we've got r squared cosine squared plus r squared sine squared. Let's factor out the r squared. And then we've got cosine squared plus sine squared, which is just 1. All right, so r squared minus 2r cos phi plus 1. No, r squared. Let's take a derivative of both sides implicitly. Take the derivative of s squared, we get 2s times the derivative of s, because we're assuming we need the chain rule. R is constant. We're not moving the sphere and we're not moving point P. Little r is constant, its derivative is 0. Minus r to capital R, all constant. 2r. The derivative of cosine is negative sine times the derivative of the argument d phi. R squared is constant, its derivative is 0. We divide both sides by 2r capital R. So we have sine phi d phi is equal to s ds over r capital R. Sine phi d phi is that expression. So now we can rewrite the potential energy of the ring we're talking about. Negative g little m, the mass at point P, capital M, the mass of the whole thing. Let's put this factor of 2 downstairs. 2s sine phi d phi. Uh-oh, I erased it. What did it say? Hold on. S ds over r. All right, so we got s's to cancel, and now the energy of the ring, negative g m over 2 r 1 over r. Oh, sorry. R is constant, ds, I forgot ds. So now we can integrate this. This is actually the small bit of potential energy associated with the pink ring in the diagram. We need the whole sphere's worth of them. So this is some differential ring, and we've got, all right, so we can integrate both sides. The potential energy of the total then is the integral of this, but this, all of this junk is constant. So we're just integrating ds. Negative g m capital M 2r times the integral of s, well, the integral of ds, which is just s. S is going to go from r plus r at the top end minus r on the bottom end. This is going to get us, let's distribute the negative, minus r plus capital R. The little r's are going to cancel, and we're going to have 2 capital R, negative g m capital M. The 2 cancels the 2, the capital R cancels the capital R, and we just have the lowercase r. And this is the expression that we would have if we assumed that both objects were points. So we get the same answer if one of them's a point and the other one is a spherical shell. Then we can assume that gravity considers a spherical object as a point at its center with that mass. What if it's a solid sphere? Well, it's just made up of a whole bunch of spherical shells, all of which behave like the mass is at the center. What if it's actually 2 solid objects? Well, if I'm a point and I look over there and there's a sphere, it all behaves as if I'm a point and it's a point. But if I'm a sphere and there's a point over there, well, if a sphere behaves like a point, the point over there could just as well be a sphere, because I know a sphere behaves like a point. So if I look and I see a point, then okay, well, it's a sphere or a point, it doesn't matter, it looks the same. So we've shown that a spherical object gravitationally behaves like a point mass at its center. Awesome. And that's our chapter on gravity. Thanks, everybody.